Welcome to Demystifying Math. This is part 5 in a video series on graphing functions that have asymptotes. In this lesson, we're going to graph the function the square root of x over x squared minus 9. Let's keep in mind what our domain is. If you look at your denominator, you will see that you cannot put in a 3 or a negative 3. But if you look at your numerator, you will see that you can't put in any numbers that are negatives. So the most restricted domain is going from 0 to 3 and 3 to infinity. We can put in a 0, so we put a square bracket on there to say 0 is included in the domain, but 3 is not. Now, if you plug 0 back into your function, you will get a 0 out. So this graph actually has an endpoint at 0, 0. Since we have an undefined value at 3, let's see what happens to the graph as we approach 3. We want to look for the behavior of the graph, or the limit, as x approaches 3. So we're going to plug in a few values very close to 3. So I chose 2.9, 2.99, and 2.999. These output values are approaching negative infinity. So the limit as we approach 3 from the left side is going to negative infinity. Let's look and see what happens as we approach 3 from the right side. So I chose some numbers very close to 3, but on the right side, 3.1, 3.01, and 3.001 give us output values that are approaching positive infinity. This graph is going to be unbounded as x approaches 3. So we will have a vertical asymptote at x equals 3. Now let's look for a horizontal asymptote. We're going to do that by taking the limit of the function as x approaches infinity. I'm going to rewrite the function by dividing each and every term by x squared, and then simplify. So if you have a constant over a variable, it doesn't matter what exponent that variable has, unless it's a negative. If it's a positive exponent, that factor or fraction is going to head towards 0. So we're left with 0 as our limit, which means that as this graph goes to infinity, it approaches y equals 0. So y equals 0 is going to be a horizontal asymptote. You don't need to be concerned with what happens as it approaches negative infinity in this case, because our graph doesn't have, and it doesn't exist over there. Remember, it starts at 0 and goes toward positive infinity. We also found that endpoint at 0, 0, so that's actually lying on our horizontal asymptote. Okay, now that we have our asymptotes, we're going to look for where the graph is increasing or decreasing. We're going to do that by taking our first derivative. So I let my numerator equal u and my denominator equal v, and then I took the derivatives of both of those. Then I plugged into the quotient rule, so I have vu prime minus uv prime all over the square of the denominator. Now what I want to do is factor out the 1/2 x to the negative 1/2. So for the first term, that's all gone, and I'm left with x squared minus 9. For the second term, I'm actually dividing this. 2 divided by 1/2 is going to give me 4. And the x to the 3/2 divided by x to the negative 1/2, you would subtract those exponents, so you would have 3/2 minus negative 1/2, or 3/2 plus 1/2, which is 4/2, which is 2. Alright, so now what we're going to do is take the 1/2 x to the negative 1/2 and bring it down to the denominator. So it's going to be 2x to the positive 1/2. And then in the brackets here, I just simplified. Now I notice that I have a common factor of negative 3, so I factored that out. And I rewrote my x to the 1/2 as square root of x. Now in this format, it's easy to see where the critical points are. So they're 0, 3, and negative 3. So here at 0, you would have it undefined. At 3 or negative 3, it would be undefined. But we're going to ignore the negative 3 because our domain starts at 0. Our numerator is never going to equal 0, again, because you have an x squared plus 3 here, and x squared is never going to equal negative 3. So our critical points are at 0 and 3. Now, if you look at your first derivative, the numerator is always going to be a negative number. Again, this is always going to be a positive times a negative, so we get a negative. The denominator is going to be positive for any numbers that are greater than 0. This is a square, so that's positive. This is the square root of a positive number, or 0, so it's going to be positive. And we have a negative divided by a positive. So it's always going to be decreasing on these intervals. Okay, so we're going to take this and look for our concavity of our graph now. And that means that we have to take the second derivative. So our numerator is 3 times x squared plus 3. Negative 3 is a constant multiplier, so we can ignore it. Take the derivative of the function x squared plus 3, and we get 2x, and then multiply them together. For the denominator, it's not quite so easy. So it's actually a product, so we're going to use our product rule on it. So I'm going to call it a product of 2 times the square root of x times x squared minus 9 all squared. So I took the derivative of the s and the t, and I simplified it. So since this is a product rule, we're going to do uv prime plus vu prime. Or in this case, st prime plus ts prime. So we have 2x to the 1/2 times the 4x gave us 8x to the 3/2 times the x squared minus 9. And then we're going to take this x squared minus 9 all squared and multiply it by the s prime. Then we want to simplify that. So I'm going to factor out the x to the negative 1/2 and one of the x squared minus 9. So that leaves me here with 8x squared, and this is factored out. And then over here, the x to the negative 1/2 got factored out, and so did one of these, so I'm just left with an x squared minus 9. Now I brought the x to the negative 1/2 down to the denominator, and in the brackets here I combined like terms. And then notice that I have a common factor of 9, so I factored that out, and I'm left with x squared minus 1. Okay, so now what we want to do is go back to trying to find our second derivative, because all we've done so far is find the derivative of the numerator and the denominator separately. So this is going to be a quotient rule. So what I did was simplified b prime. I just rewrote it so I have the square root of x as x to the negative 1/2. A little bit easier to work with. So we're going to do vu prime, which is the x to the 2x to the 1/2 times the x squared minus 9 squared times negative 6x. And then minus uv prime. So this was minus and this is a minus, so that gave me a positive here. And then I multiplied the 3 times the 9. I have the x to the negative 1/2. I have the x squared plus 3 and the x squared minus 9 and the x squared minus 1. Then I squared the denominator, so I'm squaring 2. I'm squaring square root of x. And I'm squaring x squared minus 9 squared, which gave me x squared minus 9 to the 4th. Then we're going to factor again. So the 12 and 27, I factored out negative 3. And then always factor out your lowest degree here. So I'm factoring out x to the negative 1/2. And then I have a common factor of x squared minus 9 I'm going to factor out. So dividing the 3 into the 12, I've got 4 positive. Dividing the x to the negative 1/2 into x to the 3/2 gives me x squared. And I'm left with 1 x squared minus 9 factor. Then I'm going to divide the 3 into the 27, which gave me a negative there. And I still have the x squared plus 3 and the x squared minus 9 left over. Now I'm going to bring the x to the negative 1/2 down to the denominator. And what I did in the brackets here was I distributed the 4x squared, and I FOILed all this out and multiplied by 9. Then what I did was I combined like terms in these brackets here, so I'm left with negative 5x to the 4th minus 54x squared plus 27. And then since I had so many negatives, I went ahead and distributed the negative back into the parentheses here. So I got this as my second derivative. If we're going too fast here, just go ahead and pause your video and come back to it in a few minutes. Okay, so we want to look for critical points on our second derivative. So looking at your denominator, if x is 0, it would be undefined. If x is 3 or negative 3, it's undefined. Again, we're going to ignore the negative 3. Then we also want to look to see where our numerator is equal to 0. And our numerator is going to equal 0 where that 5x to the 4th plus 54x squared minus 27 is equal to 0. Since that's a quadratic type, we're going to use our quadratic formula. Now the quadratic formula is not going to give us x, it's actually going to give us x squared in this case. So plugging into the quadratic formula and simplifying, I have negative 54, and I'm just using the plus sign here because my domain starts at 0, so I'm really not interested in a negative solution. So I'm only going to work with positive. Alright, and then what I got was an estimate for x squared, and then I square rooted it, and I got around 0.69. So at 0.69 we have a possible change in concavity. So we're going to put that on our number line and test points between and beyond those critical points. So I chose 1/4, which is 0.25, which is between 0 and 0.69. And I chose 1/4 because I have a radical here, and it'll make it easy to take the square root of that and then cube it. So there's not quite so much estimating going on. But I plugged that 1/4 in, and I got out a positive number, so that tells me it's concave up on that interval. Then I chose a point between 0.69 and 3, and I chose 1, so that one was really easy to work with as well. And I got out a negative, so it's concave down there, so we actually do have a change in concavity at that 0.69 value. And then I chose a point beyond 3, I chose 4, and I got out a positive, so it's concave up there. Now at 3, we don't have actual point on our graph, it's an asymptote, so there is no point of inflection there. But there is one at the 0.69, so we're going to go ahead and put the 0.69 into the f of x function and get an output value. So I have negative 0.0976 is the output there, so that's going to give me my point of inflection. Okay, so what we want to do now is plot a few points. So we have 0, 0 already, and then I chose 1 and 4 and 9. So you would want to plot those points. It shows you where your graph is anchored in what regions. Okay, so you're going to draw your vertical and horizontal asymptotes, use a dotted line, plot the points that you found, also plot your point of inflection and the endpoint at 0, 0. Between 0 and 0.69, you're going to draw a curve that's concave up and decreasing. Between the 0.69 and 3, you're going to draw a curve that is concave down and decreasing. Remember, it's continuous at the 0.69, so you have a point there, not an asymptote. Beyond 3, you're going to draw a curve that is concave up and decreasing. So go ahead and try to draw your graph and come back and check it. Okay, so here's your graph. We have this endpoint at 0, 0. We have a point of inflection here, and you can kind of see on this graph, I kind of stretched out my vertical axis so you can see it clearly, but there is a concavity here, and it's concave up, and here it's concave down. So this is your point of inflection here. At 3, you would have a vertical asymptote, and then beyond 3, you would have concave up and decreasing. Okay, thank you for tuning in to Demystifying Math.